Hello and welcome to the second video of this series. The way I want to design the series is that there's going to be two parts for each chapter. I'm going to make the first part as I'm going to try to make it as understandable as possible, meaning that I'm going to try to make it to try to keep a lot of the technical stuff out and focus more on talking about the meaning behind some of the theorems that we are going to discover on this journey, and like make some drawings and stuff and talk about them. So that's what I did in the first part, and then in the second part I want to make the second part very theoretical and focus on the theoretical results. That being said, let's start. I want to start by proving something that we've already used and we've already shown actually, but in a very simple form. If you remember the last example, we computed the probability that theta is equal to 1 given that x is also equal to 1. And the way we did that is we use Bayes' rule. Bayes' rule also has the same name as this whole topic, and it's definitely the key to inverting probabilities, because here, why do I say inverting? Because we know x and we want to know something about theta, while actually if we know theta, we do know the distribution of x. So by Bayes' rule, we can write this probability as the inverse probability, the probability that x is equal to 1 given theta, times the prior divided by the general probability that x is equal to 1, which we can write as this sum over all values of theta. In our case it was from 0 to 1, but in general I always use, I didn't mention it in this video, in the last video, I always write like, if I don't want to write out the whole thing, I just say the sum over I for all possible values of I as a kind of a shortcut. And what we want to prove is that this rule holds for densities. So the posterior density pi of theta given x can be written as the product of the sampling distribution times the prior divided by the integral of this product over all possible values of theta. And what do I mean by integral? Because this can be an integral, and it is an integral if this density here is a PDF, or in general if the prior is a PDF. If the prior is a PMF, however, we are going to talk about a sum. So this integral notation is a shortcut to saying use a sum if we're talking about PMFs, and use an integral if we're talking about PDFs. So later we might have a PMF or a PDF. The theorem is going to hold for both. It's also going to hold in a mixed case. So remember the prior can be a PDF or PMF. But the same holds for the sampling distribution. It can also have only one. We said that there's no there's no values for theta, for which for one value of theta we have a PDF and for the other we have a PMF. But it has to be either PDF or PMF as well. It doesn't mean that they have to be the same thing, and there are cases where they're not. In the case that both of these are the same, this theorem holds. But for the mixed cases, we're going to need a small distinction, a very small additional requirement. So let me just write this out. So this holds if pi and f given theta are either both PDFs, both PMFs, or pi is a PMF, so pi being a PMF and f being a PDF is also fine. But if we have the case that pi is a PDF and f given theta is a PMF, we have to be careful. Because in this case, it can be that x given theta is discrete and x, so the marginal of x, marginal distribution of x, it does not have to be a discrete distribution. We can see that on an example. Let's just say we have that theta is uniform distributed on 0, 1. So anywhere on this interval, for any subinterval of equal length, they have the same probability. And then let's just say that x given theta is just equal to theta, which we can do that. We can define it like that. And in that case, x given theta is definitely discrete because the probability that x is equal to theta given theta is 1, and for any other value we have 0. So if we observe the value of theta, obviously we know the value of x. So that means no matter what value theta takes here, any one of these values, x is going to take the same value. But it also means that x is also uniform distributed on a 0, 1 line, which is a continuous distribution. So that's a problem, and you want to exclude that problem. So how do we fix that? We demand that the values that x can take, which I'm going to denote by this x here, which I'm going to define as the sample space. The sample space is the union of the image of x given theta, of overall values that theta can take. We want it to be at most countable if x given theta is discrete and theta is continuous. Because this assures us that the marginal distribution of x is still a continuous distribution, and then we can directly imply what the posterior distribution will be, if it's going to be a discrete or continuous distribution. In this mixed case, theta just can completely change the image of x and even make it uncountable, and then we don't even know, do we have a PDF or PDMF, and that's a problem, because then we don't even know if we have a posterior density. So let's prove this. So we want to prove this using the argument of a joint density. And a joint density, which doesn't always exist, it's defined as a function, in this case our function phi, for which the probability of the joint vector theta and x being in some combination of measurable sets B and A, it's the double integral over these two sets over the density. And we don't really care about the order, because then if we have this density, we can write the marginal probability distributions, probability that theta is in some set, just as the probability that this joint vector is in this set times the image of x. And that's then just the integral over the integral of the joint with respect to x. So then our marginal distribution, which we can define as m of x, can be derived from the joint. As just this whole integral with respect to x, same way. So analogously, probability that x is in some set is just going to be the integral over the set over the integral of the joint with respect to the image of theta. And this is then the prior, right? Because the prior is the marginal density of theta. Okay, so let's show that we have a joint density. We're going to do this using Fubini. So this we know just by the definition of the conditional probability that we can write. Sorry, the sets are wrong. B times A. I don't know why I put them in this order. So this we can write by the probability, by the definition of the conditional probability as the integral over B over the conditional probability of x being in A given theta times the prior. And we already know what this is. This is just the integral over A over the sampling distribution of x given theta. And then we can just plug pi of theta into the integral because it doesn't depend on x. So we have this whole integral over x and then the whole integral over theta, which is exactly what we want. It's exactly this function, so that's how we're going to define it. And now this is where the small precondition comes in, because we want to show that we can interchange the order of integration. And for this we need a theorem called the Fubini-Tonelli theorem, which says that we can do this if we have a function which is non-negative, which is the case here. So this part is definitely larger or equal to 0 just because we have densities. And then we want, so the technical term is that we want the measures to be sigma additive. In our case, it just means that if we have a sum here, then we want A to be at most countable. Because if A is an interval, we can't really sum, we can sum over the integral, we can just sum over every positive value, but we can't change the order of summation and integration. Same thing for the other integral. For the other integral, it holds automatically because we have given that pi of theta, it's either discrete or continuous, and if it's discrete, we can just say that this set, we can just say that it's countable because we can just take all of the values that it takes. The other values we don't care about anyway. And we can do the same thing for this if x given theta is discrete, because we know if x given theta is discrete, that x is also going to be discrete. Because if we would have a sum, we would still want to interchange the order of summation and integration, which also holds by Fubini, but Fubini says that if we have a sum, we want the set over which we sum to be at most countable. So this is why we needed the precondition. The intuitive reasoning is that we don't want the distribution of x to change, in the sense that we don't want x to all of a sudden be continuous when x given theta was discrete. We don't want the kind of distribution that x has to change. Okay, so by Fubini-Tonelli we can change the order of integration, and then we do have a joint density. And then we're done, because pi of theta given x it's just, I mean, this is just the definition of conditional densities. You can also calculate this out. This is the joint over the marginal. And we know what both of these are. And that concludes the proof. So let's see what this proof implies. So let's say that we are given a prior. So we can accurately express our prior beliefs. We're going to see later that this is actually a huge problem and it's not clear how to do this at all. But let's say that we have that. Given a prior pi, if we have a value that we observe in our experiment, this function over here, it's completely determined by the value that the sampling distribution takes at this point. Because remember, this is just some constant. This is like, here we completely integrate out theta, so whatever is left, it depends on x, but if we have the value of x, it's just some constant. And a constant does not change a distribution if you have a positive constant, because we already know that the whole integral has to sum to 1, or the whole integral has to integrate to 1, the whole sum has to sum to 1, depending on what kind of distribution you have. And so really what we only care about is the numerator. And the numerator is defined by pi of theta, which we already know, and then by the sampling distribution of x given theta. So this is entirely determined by the value which is taken. And so because this depends on because the resulting distribution depends on theta rather than x, it's common to write this as a function L of theta given x, which just the difference is only notation, and it's defined as the likelihood function of theta given x. And this has some huge implications, because if you think about inference, which is the goal of statistics, so what does inference mean? In our case and in this series, we're going to, inference is a very, very broad thing, and we can just divide this up in 3 categories. First of all, so in inference in our case is what can we infer about theta given x? And in our case, we're going to be focusing on estimation. So what is the best kind of approximation of, for example, theta when we are given the value of x? So we're going to measure it by some loss function L of, so this is like sort of a bit of foreshadowing. We're going to see later if this is a lot of letters for you. All of these letters are going to be explained in the later videos. So we have some estimated delta of x and some value of theta. And then we have a loss function over the whole thing, and we say, okay, if the estimator is very close to theta, the loss function is very close to 0. And we want to evaluate this loss, and the way we evaluate it is we can, for example, compute the probability that, this is not what you usually do, but you could think about this, like, for example, what is the probability that the loss is going to be very high? Like, high is some very high number n, given that we observed x, because we can choose the estimator depending on x. Then next thing that we're going to do is prediction. So we observed x, and there's something else, some other random variable z, which is also something to do with theta. And we want to compute some probability, for example, that z is larger than little z. And the last thing can be hypothesis testing. One example for this is our last example. What's the probability of some event theta 0 happening given that we observed x? All of these can be calculated using the posterior. So actually, we can define what is known as the likelihood principle. If we have, remember we just had that the likelihood function of theta given x, it completely determines the posterior distribution. So if we have two values, two outcomes, x1 and x2, and they have the same likelihood, or even that the likelihoods are multiples of each other, so there's some c larger than 0 for which one is the multiple of the other. Then inferences, every kind of inference based on x1 or x2 should be the same, or even have to be the same. Okay, where does the c come from? Well, if you plug c times something in here, and you plug c times something in here, the c cancels out, so we don't care about the c. This is a very fundamental principle of Bayesian statistics. And the rest of this video is going to be taking this principle and seeing what other kinds of principles there can be derived from that we care about and that we want to have. And we're going to see that's going to be quite a few of them, which is going to be very useful. I'm going to start with a corollary of the likelihood principle, just immediately implied, which is the stopping rule principle. If we have a value of some likelihood, we don't care where it comes from. So, okay, that was a bit quick. So, let's say we toss a coin just a couple of times, and every time, like the first coin toss is tails, which we denote by 0, second is tails, and so on. And we toss it 5 times, and on the 5th time we get head. The probability of this event, or actually the likelihood of the whole sample, f of x1, xn, we can just ignore theta for a second. In our case we have x5. It's actually for every single one, every single kind of combination which is possible, it's 1 over the possibility of combinations, which is 2 to the power of 5. And then consider we have a different experiment where we toss a coin until the first head. And then, so we toss it, we check, is it head? No. Toss it again, is it head? No. And we keep going, and then on the 5th time it's head. Then the likelihood of this, it's the same. It's still 1 over 2 to the power of 5. Because we have 1/2, the likelihood of this particular event is the same. Because we still have 1/2 is the probability of the first one being tails times 1/2 and so on. But the general likelihood, so for our case, these are the same. But the likelihood of any case is the geometric. So if we have some event which is equal to 0 up to n, then the probability of this event occurring is actually 1 over 2 to the power of n. So we can say that this is f2, and then this one for any particular event, because we said before and we tossed the coin 5 times no matter what happened, the probability is 1 over 2 to the power of 5. So we have 2 completely different sampling distributions, but the likelihood is the same. So no matter what kind of, so here I ignored theta, but if we just add theta everywhere, let's say we have like an unfair coin and then we don't have 1 over 2, but we have theta to the power of 5. Inferences based on any prior are the same. So how do we generalize it? This example, no matter what kind of stopping rule we have. So if we have, that's why it's called a stopping rule principle, if we toss a coin like 20 times And if we compare it to tossing a coin until some event based on the coin happens, we don't care what kind of event. This time it was the event that the coin is head. It can be anything. It can be that the sum of the coin is 20, or that there's no head on the 20th occasion, whatever. If a stopping rule is made, so if there's a stopping rule, what is a stopping rule is what I just described. It's like some function based on the prior values. We don't care. We can stop the experiment for any reason whatsoever. The resulting inference will be the same. So we can say it has the same consequence as any other sample, any other stopping rule, or we can say in general any kind of sample of the same length. So the choice of the stopping rule doesn't matter. This has huge implications. Why? Let's say you have a cancer study. So you want to choose some new medication. See, I'm going to fail at drawing this so bad. So we have some new pill C, and you want to test if this pill works. So you have a study, and some guy or girl takes this pill, and he takes it on first day, second day, and so on. You are not allowed, if we think about classical statistics, there is some problems about checking whether this guy gets sick from the pill and then stopping the study, because this changes your sampling distribution, and in classical statistics that is actually a problem. If you want to know why, you have to take a course on classical statistics. But with Bayesian statistics, we can check every single day. We can say, okay, day 1, is this guy healthy? Yes, that's good. Day 2, yes. And then we check on him every single day, and on the kth day, we see, oh no, this guy is seriously sick. And then immediately we cancel the study. And obviously you have to do this because of ethical reasons either way, but we can cancel the study, and that's fine. That does not change our findings. It at least doesn't mess up anything. It's the same as if the sample was taken on any other occasion. It's the same as if you would have said after the kth day we stop, which we would have to do either way if he turns out sick. And so that's good. And it has huge consequences. So, not the best transition, but some other things that are good. So, the other principle is going to be pretty theoretical in nature, but it's also going to be pretty important. Just in general, in statistics in general, like in classical statistics as well as in Bayesian statistics, it's actually a concept of classical statistics. It has been developed by Fisher, if I'm getting this right, and it's a very nice concept, let's say that. It's a concept of sufficiency. What does sufficiency mean? If we have a very long sample, let's say, again, tossing a coin n times, and we get some result, we don't care. If the sample is very, very large, like some huge M, really, really large, it would be nice if we could just summarize this in a very, very simple way. If we could just take all of these values and we just take one value instead, and we don't lose any information. It turns out that this is the case, and the statistics the kind of summary measures that can do that are defined as sufficient statistics. So a statistic T, statistic just means function. Let's just say function, measurable function. A statistic T of X is sufficient. Now I'm not going to use this intuitive definition, but I'm going to use the mathematical definition, which is that the distribution of X given theta, of X given T of X does not depend on theta. So there exists some probability measure, P, such that the probability of X being, again in some set A, given T of X, and now I'm not going to write given T of X and theta here, because it gets a little bit confusing, and also because theta can actually mean, we have this definition of conditioning on theta in Bayesian statistics, but this concept is actually used in both, and you can just say you think about some fixed theta, it doesn't matter. So this probability of X being an A given T of X given theta is equal to this probability measure of X being an A given T of X, and theta has disappeared. So no matter what value theta takes for all values of theta, the probability distribution of X given T of X is the same. That's weird. That's a weird definition. Why do we use this definition? If you think about the probability of X being in some set, we can express this as the expectation. So I'm writing this E for expectation with respect to theta over the conditional probability. Right, that's just the definition of the conditional probability. And if T is a sufficient statistic, we can now remove the theta. And now we see that this function here, this only depends on the distribution of T of X, because it's a T of X measurable random variable. This only depends on the distribution of T of X, because it's a T of X measurable random variable. And again, the distribution of T of X depends on theta. So if we know the distribution of T of X given theta, we know everything. In our example, so this is the binomial distribution, we have some fixed n. We can just take the sum, we can just combine this whole thing into one value. We can say T of X is the sum over all values. And then this is a sufficient statistic. Why? Because the probability that X is equal to some A, we have a discrete distribution, so we can summarize this to some small a, and then everything the set is just the sum of all of these probabilities. Probability of this, so the coin is tossed with probability theta, that's what I mean when I denote theta. The probability of this given T of X, if we know the sum, first of all, this is 0 if the sum, here A is some vector, X is like a vector of x1 to xn. denoting all of these coin tosses. If the sum over AI is not equal to this sum, it's just 0. Because then it's impossible that this event occurs. On the other hand, if the sum of this is equal to xi, every kind of possibility has the same probability, because we don't care about the order, because that's what the binomial distribution is defined as, tossing a coin without caring about the order. Sorry, that was confusing, because every order has the same probability. That's what I want to say. So this here, first of all, the sum, it doesn't care about the order, and every event has the same probability. So this here has the same probability as this event. So we can just sum over every possible I, every possible, or let's say every possible B, such that the sum of bi is the sum of the xi, which is t of x, and this is the amount of all of the possibilities, and a is just one part of this. So the probability of a is 1 over this sum. Both of these expressions have nothing to do with theta, so we can summarize the whole sequence of coin tosses into just one value, which is the sum. That's much smaller downsize than whatever the size of n is. And then the sufficiency principle says exactly what I just said. If we have two values, x1 and x2 of our sample, and the sufficient statistics of both of these values are the same, inferences are the same. So any inference based on the values x1 and x2, even though x1 and x2 might be different. So this might be an example. x1 and x2 are different, but their sum is the same. So any kind of inference that we make on theta, it's the same. The sufficiency principle follows from the likelihood principle. Why? It follows from the likelihood principle because of a very important theorem called the factorization theorem. And this theorem is actually, intuitively, it makes a lot of sense. It says that the density of x given theta can be expressed as the density of t of x given theta. So first we calculate the value of t of x, or the probability of t of x given theta, and then based on this we calculate the probability of x given t of x, if and only if t is sufficient. I'm only going to give an idea of this proof. The exact proof, it's a bit messy. It's on Wikipedia, so I'm just going to give the link to the Wikipedia article for the proof, for the detailed proof. But for a simple proof in a discrete case, we're just going to look at f of x given theta. We're going to prove two directions. So for the first one, let's assume that t is sufficient, right? Because we have if and only if here, so we have to say that one implies the other and the other way around. So if t is sufficient, first of all, this holds in both cases. This here can be written, so we have a discrete case, so this is just the probability that large x takes some value. Maybe I should write this out. This is the probability that large x takes some value small x, given theta. This is actually the joint density in x and t of x, because this here implies that t of x is small, sorry, not small t, but t of small x. Yeah? So this actually, these are the same. We know that we can write this. We've seen this in the last theorem. F of x given t of x and theta times the prior distribution of t, which I'm going to denote by g. And since t is sufficient, this part over here has nothing to do with theta. And I'm just going to denote this by h. And then we have exactly the form that we want. So we can now do the other direction. For the other direction, we want to show that if, and I didn't explain this very well, so I'm saying this is if and only if, in the case that we have some h larger or equal to 0 and some g larger or equal to 0, which are functions which fulfill this. We don't necessarily need them to be the densities, but it's going to turn out that they are the densities which I described earlier. So we're going to assume for some g and h larger or equal to 0, f of x given theta is equal to these two functions. But we don't yet know what they are. Now, it's still the case that the joint f of x and t of x is equal to the marginal of x, yeah, for the same reasoning as above. And then the distribution of t given theta, which we want to calculate. So if we insert some value, and let's call it g prime, this distribution, if you insert some value t for t of x given theta, we can calculate this distribution by summing over the joint. So summing over all values of x such that t of x is equal to small t. And we're just going to insert this. Now this function h, it actually only depends on x, right? Because we insert x and t of x, so we can just write it as a function of x in total. Right, because this notation is it's just a shortcut to express what we mean, but really h is just a function that takes one value, which is x. It does not take the value t of x. But g we can write as a function of t of x. So we sum over this whole thing. And then since g is a function of t, we can exclude g. And we sum over h. So this is the density of t. And then we know that the distribution of x given t of x and theta, which we denote by h prime, it's just the joint. So yeah, it's the joint, which we have here, divided by the marginal. But, and okay, we can write h of x given t of x. This part here cancels out. And the other part over here does not depend on theta. Sorry. The other part over here, it does not depend on theta. Yeah. So this implies that t is sufficient. This is the case for the discrete one. For the other one, look at the Wikipedia article. Makes things a bit complicated because the distribution of t, by the same reason we had for the last theorem. It does not necessarily have to be discrete. Okay, so we had this factorization theorem. And this immediately, if we have the likelihood principle, implies the sufficiency principle, because if we have x1, x2, such that t of x1 equals t of x2, and this implies that f of x1, so this is the likelihood, right? We can also write this as L of theta given x1. It's equal to, first of all, this function, and this function is proportional to the other one. We see that by writing this. So first for this value, here we can exchange the x1 with the x2, and then writing, because we want the other function here, so first we write h of x2 given tx1, tx2, and then we just multiply it by what we want to have, which is h of x1 given tx1 divided by h of x2 given tx2. So this here is equal to t of x1. So these two functions, they're the same. And this over here is just c in our likelihood principle. If we go back, well, I can just write this down again. If we have that L of theta given x1 equals L of theta given x2 times some constant c, then we have the same inference. And c is a constant. It's, if we know x1 and x2, c is a constant. It has nothing to do with theta. So the likelihood principle implies the sufficiency principle, and there's one other principle which I'm going to mention, and we're going to prove that, and we're going to finish with that because this video is way too long already. But I'm going to also make a small remark about why do we care about these principles, because especially the sufficiency principle, it's a bit mysterious, and I'm going to explain soon why it's important. So the other principle is the conditionality principle. The conditionality principle says it's very, very simple, very simple, but it can be very it has strange consequences. The conditionality principle says if there's two experiments, let's call them Xi1 and Xi2, and there's a 50-50 chance, it doesn't have to be 50-50, it can be p and 1 minus p, that I get Xi1 and there's probability 1 minus p that I get Xi2 as an experiment, and then I know that I get Xi2. So like there's some, I get nominated for 2 studies and I can only do one of them, and I get lucky and I get Xi2, or in general Xij. The evidence of this experiment, which I'm going to denote by j and Xij, so whatever output Xij I get, if I know the value j, so if I know actually which experiment I get, the evidence that this experiment gives me is the only relevant one. And this is very important, although very obvious. It doesn't matter that there was a probability of p, even if it's like really high. If there's a 95% probability that I would have gotten the first experiment, I got the other one. So any kind of evidence that I get, it's only relevant for the other one. I don't care about the first one. what would have happened in the first one. And yeah, we can immediately see this, that this follows from the likelihood principle. Why? Because our likelihood function, it's the same as the likelihood function from the original experiment. So let's say Lj, but with some constant, either p or 1 minus p. So I'm just going to denote this by pj. And then this is again our c. So for Bayesian statistics, this principle follows immediately. Why is this one important? I mean, it seems very obvious. It's not obvious in classical statistics. It still holds as one of the... It's a very well-known example for where it's clear that you actually want to use some of the information that you have, namely the information that of which experiment you got. So you first say, okay, which experiment do I have? Then you denote p-value and confidence interval and so forth. If you want to choose the p-value before you even know which experiment you have, you're going to get different p-values, even though it doesn't matter which experiment you would have gotten in the long run. Alright, and okay, so we have conditionality principle and sufficiency principle, which seem kind of random. Why are they important? They're important because there's a paper which says, I'm going to put a link to the paper in the description, that these two very, very simple principles imply the likelihood principle. And then this makes it look like Bayesian statistics is kind of a necessity if you want to hold on to any kind of principles. Unfortunately, this theorem, well, or fortunately, this theorem has been claimed to be disproven by a more recent paper, and then there has been several papers on why this paper is false, and then there has been replies from the author of this paper and so forth. The author is absolutely brilliant. She also has a page where she I hope I'm putting this correctly, where there's a lot of entries about statistics, also about philosophical discussions about what is statistics used for, because the argument is actually somewhat philosophical. It hugely depends on what you mean by inference, what you mean by statistics. And I also wanted to mention this just because it's a very nice example of how even kind of old results that we've already known can be disproven at some point, and how broad the world of statistical philosophy is. Because statistics, we actually want to apply it, and these mathematical arguments, they are very important, but it's also very important to think about what is the actual use of statistics, how should we use statistics. And why am I mentioning this now? I'm mentioning this now because all of this is discussed in some depth on the webpage of the person who wrote this paper. So go check that out. And thanks so much for listening, and see you next time.